Hello everybody. Cool to see so many people here. I've got some fierce competition from John Skeet now, so lovely to see all that you're here. I'd like to introduce myself first. My name's Francis Paulin, work at WebStep. I'm a full stack developer. And I'd like to get started by showing the reason that I got into Akka and the things that I'm going to talk about in the first place. So I work at ABB. They've been my client for the last 2.5 years. Worked on various different projects there, and the most recent project that I've been set to work on is to build the front end for an electrical simulator. So that's basically a simulator that simulates electrical circuits, albeit rather large ones, so huge generators and motors and things in factories or oil rigs, things like that. And they've been so kind as to let me demonstrate this. So I'll show you what we've built, and then I'll go through some of the technology and how we got there, but with a slightly simpler coding example towards the end. So plug this in. Can you all see? So what we're looking at here is an electrical system that is being simulated. Off to the side here you can see all the changes that are going on. So that will be voltages that are changing, currents that are changing, changes in the frequency, and these changes then get pushed to us every 10 milliseconds. So there's not a lot of time between each tick to actually render stuff out. So this then gets piped into the actor system as messages, and then we do some things with the messages, and then we send them up via Signal R to our Redux, and then it gets rendered with React. So what this is really useful for is, for example, if you want to do training to see how a system will react to different user inputs, or for example, if you need to take out a generator for some planned maintenance, you can see what will happen if I just disconnect this generator on the spot. So we can try and do that now. So we've got 3 generators that are connected, and we can see what's going on here. And you can see that they're all within the specified load that they're rated to. But if we close this switch here, you can see that immediately the load becomes too high for the generators and they're starting to struggle. So then you could then find out that if we then take out what I happen to know is a very high load, and then disconnect the generator, then we'll still be fine. And that can also be used to test systems that do this automatically, so-called load shedding systems, so that you can program that these motors aren't particularly important. So if we haven't got enough power, then just cut them out. So it's quite cool. It's almost like a game. So it's been really fun to work with. So that's what we've built, and now I'd like to show you how we built it. Can you see the presentation? No, you can see my desktop. Up better? So, some statements to get us started. Distributed systems are hard. Writing applications that scale on demand is hard. And threading and shared state can be nothing short of a nightmare. Some of you are probably good at this and don't think it's hard, but I find it incredibly difficult, so I appreciate having frameworks to help me do this kind of stuff. So that leads us to Akka NET. And as we were researching technology to use to make this simulator, I was listening to .NET Rocks and an interview with Aaron Stannard. And we were talking about Akka NET. He's one of the core contributors. And I thought, well, this sounds really cool, and it sounds like it could be useful for the thing that we're building. So I looked into that, and turns out it was a good fit. And if you look at the website, you have this little thing up there that says, "We are reactive." And what does that actually mean? Well, if we click on that, we get sent to the reactive manifesto. And that is 4 principles or traits that define a reactive system. So the system should be responsive. So that means that if a user, so a user could be a person, it could be a machine, it could be anything, asks the system something, it should get an answer. It might not necessarily be the answer that you wanted, so it could be that the database is down or something like that, but you should at least get an answer. And also, the system should be elastic, meaning that in response to high load, the system should be able to scale itself so that you can continue to serve your customers. The system should be resilient. Errors happen, we all know that. It's impossible to make a completely fail-safe system, but the system should be able to heal itself and deal with that and not just throw its items in the air and give up. And also, it should be message-driven. So that basically means that we send messages to each other, and that allows us to do some interesting things, such as having location transparency for our code, in terms of that it can be running in different places. But we'll get more into that a bit later. So what exactly is the actor model? It's a conceptual model to deal with concurrent computation and a method of concurrency in which the universal primitive is an actor. And that might all sound a bit fluffy, but just as in object-oriented programming, where the class could be seen as the universal primitive, then in actors, then it's the actor that's the universal primitive. And there are many similarities in terms of, like, if you were coding object-oriented style, you would make a class for things, and in many cases you would make a corresponding actor. And it's not a new idea. It was first published in the early 70s, so along with many things in computer science, things come back again much later. So what exactly is an actor? Well, an actor can be pretty much anything you want it to be. An actor is persistent, so it's not like a thread that when it's done its thing, it just like disappears off it. The actor will hang around and wait for messages unless you kill it or it dies in other ways. And actors can have internal state, which is very useful. And an actor has an address. So, like you would have a reference to an object, here you have an address to an actor. And an actor also has a mailbox. So if you send a message to an actor's address, it will end up in the mailbox. And the mailbox is basically just a queue. So each actor has its own queue and then handles those messages. So what can an actor do? Actors will then react to messages that are sent to the mailbox. An actor can send messages to other actors, but also to itself. An actor can create new actors, child actors, and an actor can decide what to do with the next message. So an actor has this notion of behaviors, so you can put it in a different state, and then instead of having lots of ghastly conditional logic, so if this then that, then you can just put it in a state, and then it will do what you've decided to do in that particular state. So that enables you to have much cleaner code. Some very important principles that I like to observe, as always, the single responsibility principle. You don't want to have some kind of God actor that does everything, just like you don't want some kind of God object that does everything. Only interact with an actor through messages. If you start mixing in other ways of communicating to the actor, and there are exceptions, but only in rare cases, then all of the guarantees that the actor system provides you go out the window. So you don't want to be doing that, because that can lead to unsafe things happening. And exactly one message is processed at once. And that's one of the most important and useful traits that you have with an actor system, because that means that when you send a message to an actor, when that's processed, you can view that actor as a single-threaded program, even though you may have multiple things going on at the same time in different actors. And you will never then have to be worried about race conditions in your actor unless you do weird things that could, of course, it is breakable. You can shoot yourself in the foot, but if you follow these principles, then you should be okay. And along with that, messages must be immutable. You don't want messages suddenly changing in transit or something, because then also you can have unexpected side effects. Actors live in a hierarchy, so all actors have a parent that supervises them, and that also goes for when you make an actor at the root level, there will be system actors that supervise them again, so there will always be supervision. And an actor can send a message to any actor independent of its hierarchy. And that doesn't necessarily mean that you should do that, but you can, and it can be very useful. And you should let children do dangerous things. And from a parenting point of view, that might sound a bit scary, but you want to send scary things further down the chain. And I've got a picture here that we can use to show. Because if actor 1 sends a message to actor B1, and what it wants to do with that message could potentially be dangerous. For example, it might do something over a flaky network connection. It might be doing some computation down here from data that you know might not be quite all right. So instead of doing everything in there and then risking that one blowing up, what you can do is that you can delegate it to a child, and then if something goes wrong, then the exception is sent back here, and then you can decide in B1 what do you want to do if something goes wrong. So you could then choose to restart C1, or you might choose to restart C1 and C2 because there's some connection there. Or if B1 has no idea what to do with that exception, it can just send it further up the chain. And then, for example, up here, you might decide to restart the whole lot here because that could be seen as one unit. It depends. But that's also very useful, and that's how we create systems that can heal in the event of things going wrong. So to create the actor system itself in Akka, use the static create method on actor system. And you notice here that I've got two different variants of that. We have one that takes in the configuration, and then we have one that doesn't. And they're both the same, really. It's just that with the one that doesn't take in an explicit configuration object, that will then read the configuration from your app config or web config or other places that you can put it. You can use the application settings.json if you're using ASP.NET Core, but you'll have to write a little thing in between there, which we've done in our project, to get it to work, because that isn't supported out of the box, but I'm sure that will come in due time. So if we look at this piece of code here, it's a very simple bank account. So if we look at that, then we can see that if multiple threads try and do this, you could end up overdrawing the account because two people could be mutating the balance at the same time, and that would be pretty bad. So you could stick a lock around it, but in my opinion that's quite ugly, and the lock of course isn't part of your logic. It's not interesting. That's just because it has to be there, so it just clutters. So what we can do instead, if we implement this as an actor, we have the exact same algorithm, but instead of a method, we receive a message, which in this case is just a simple int. And the beauty of this is that because only one message is processed at a time, that means that you'll never be able to send in two things simultaneously and overdraw the account. So to create an actor, there are two steps, and it might seem a bit involved, but you get used to it after a while. First, you need to create what's called props. And props are like a blueprint or a factory for the actor, but it doesn't actually create the actor. So you send in a lambda that is run every time the actor starts, and then it calls new client bridge actor and then sends in any dependencies that might have. And then the actor is actually created by using the actor system or the context.actor_of, send in the props, and then you pass in a name. And the name here is optional. It will be assigned a name if you don't give one, but if you don't give one, it will be some name that is not as obvious as it might be, and it can be useful to have names if you want to do routing, for example, because then you can have that one under that one, and if you have some kind of gibberish name, then you won't be able to do that. So when possible, always give a name. We talked about that actors have addresses, and the address may be to a specific actor, but it could also be to a load balancer / proxy kind of object, or no, sorry, actor. So for example, if you're doing clustering and you say that you want to deploy 5 actors of such and such on a remote machine, then you would have one address to all of that, and then you could choose what kind of distribution you want. Do you want a round robin, or do you want to send your messages to the actors that have the shortest queues? There are many options that you can use there, but just be aware of that the address might not always be to a specific actor. And the address looks something like that in its simplest form. So it's the protocol, and then the name of the actor system, and then /user, like we saw on the picture of the hierarchy previously, and then the name of the actor. And that will be more complicated if you're doing remoting, because then you will have demo actor system at the host name. And we'll look at that a bit later. And this is what provides us with location transparency. So your code doesn't necessarily show at all that things can be in different places or deployed on different machines, but you can change it through configuration afterwards. So sending messages to actors. There are 2 ways that you can do that. Either you can use tell to send a message, or you can use forward, or you can use ask. And when you tell an actor, you send the message, and then you send in the context here. And self is the default, so you don't actually have to specify it if you want it to be yourself. But you could want to send a message on behalf of somebody else. And that is basically what forward does. Forward is the same as saying fooActor.tell message and then sender as the second parameter here. So it's just shorthand for that. But you can also use ask, which can be useful in some cases. But when you use ask, then you say, I would like you to give me something within this time span here. But that also means that the actor can't do anything and respond to other messages during that period. So you're basically locking the actor. So you lose some of the benefits of the model itself by doing that. So only do that when you absolutely have to. Parents know about their children, as one would hope, seeing as they made them. And they can also, of course, communicate with each other. But you should limit knowledge between cousins and below. And the reason you want to do that is because if this cousin 1 here would like to speak to cousin 2, then you have a dependency between them here. And it also means that it would be harder to refactor if you, for example, wanted to change this and you wanted to put whatever cousin was doing into child 2, then you would have to go into here and change, and it would be a lot more work than it would have to be. So what you could do then instead is that this one here could send to child 1, which could then forward to parent, that could forward to child 2, that could forward to cousin. And that might seem a bit involved. But what's cool then, because you forward it all the way over there, then when this one wants to respond, you can just say sender.tell, and it will go straight back there because it's been forwarded all the way around, and the sender has been passed on all the way. And you also have some lifecycle hooks in an actor which you don't have to use, but you can use if you want to, for example, do some cleanup before an actor is shut down. And then you have the pre-start method, which is a bit special. So it's almost like a constructor, but it's only run the first time an actor is created. So if an actor restarts, that will get run as well. But you can see that in post-restart, the way it's run is that post-restart calls pre-start. So if you have something that needs initializing once, but you don't want to initialize it on subsequent actor restarts for whatever reason the actor has to restart, then you can just override that and then take away the pre-start call, and then it will only get run the first time by the actor system. Switchable behaviors that we mentioned slightly before, they are really cool and super useful. So in this case here, we have an actor that has two behaviors. It has A behavior and B behavior. And it starts off by, you say, become A behavior, and become just takes a function that has no parameters, just a void method. And it will then do its thing when it receives a string, and it will print out from A behavior. But then it says become B behavior. So next time a string has been told to this actor, then this code will run. So that means that you can build quite complicated state machines like that, but without any ifs and buts at all, which is really, really useful. And there is also a version of this called become stacked. So if you, for example, connect to something, but then you want to go back into the disconnected state, then you could say become stacked and then in the connected state, and then if it somehow disconnects, you could just say become unstacked, and then it will go back to the previous state, so that you don't have to keep track yourself of what state you were in before. If you want, you can just pop that onto the stack, onto the behavior stack, and then use that to navigate backwards and forwards. And we use that quite a lot in the simulator, and it's been very, very useful. Remoting. So I've mentioned this a couple of times now, but in Akka, then we can run our actors on any machine, not just local machines. It could be a machine on the other side of the world. For example, if you have a actor model running on a little computer that doesn't normally consume many resources, but sometimes you need to do this massive job or something like that that needs lots of CPU power, that you could just offload that onto a different machine, do its thing, and then you could just kill the actor afterwards if you wanted to. Security. Up until Akka 1.2, there was no security when you sent messages backwards and forwards, so that was all in plain text. That changes in Akka 1.2, so you now have TLS. And one thing that you need to be aware of when you're doing remoting is that your message needs to be serializable, because otherwise it, of course, isn't going to work across the network. And mentioned it slightly before, you can do clustering, so not just deploy one actor, but you can make clusters of actors that will then appear as one actor, but actually be many more. So, which leads us to our demo. And I'm terrible at drawing things on the computer, so I just drew a little sketch here, but I hope you can read it. So we're making something that's quite similar to the simulator system, in that we have a message producer here, which is just a console application that produces messages containing the numbers -1 to 16, I think. It puts them onto a queue, and then an event is raised on the other end to the listener, which is a queue actor. That then receives it starts publishing messages up to the Fibonacci actor. So that then just gets the numbers -1 to 16, and then it actually has to compute the Fibonacci series for that number. And that is, of course, a very scary operation, because if we get in -1, that is invalid, so that will then cause our actor to throw an exception. So we've set up the Fibonacci actor here to observe this one here and look after it and restart it when it needs restarting. And afterwards, that then pushes its messages to the client bridge actor, which serves as our bridge between our backend over SignalR up to the client, where you can then have n clients that sit and watch the Fibonacci series being computed. So this is probably the world's most over-engineered Fibonacci program, but it is what it is. So let's look at some code. I have to change to duplicate. Can you see? Is it okay on a black background, or shall I change it to a white background? Yep. Aha. I'm completely lost now. Tools. Ah, there we are. Thank you. No, this doesn't look. Am I actually running some code here? This doesn't look like it normally does. Ah! Options, there we are. That looks more right. Light. Is that better? Oh, oops. There we are. So, we have our message producer here that uses very secure cryptographic stuff that I don't understand to generate these numbers. And then it pushes them onto the queue. And that is all this program does. So if we then move to the web application, we go to the startup class. This is an ASP.NET Core app. And we go to the configure services. So we need to add two things here. We need to add a service here that can get hold of our SignalR hub, because the Akka system will need some way to get hold of that. And that is then used by the iHub context accessor that will actually provide us with our hub. And we need to enable SignalR. And down here we then pass in a function that we can use to then get this SignalR hub, and then we say demo actor system.create, and if we can just look at this quickly here. All it does is just give you the hub, and we can look at that quickly. The hub here does nothing. Because we're only pushing data from the server to the client. Excuse me. There are no methods in here that can be called from the client, but if we were doing this both ways, then of course there would be methods here that we could call. So if we go into our demo actor system here, then we send in our hub context accessor that we just made, and then we take in some configuration. Well, actually, at the moment we don't, because we haven't made any, but we'll get to that a bit later. So we're building three actors, or making three actors. We've got the client bridge actor, which is the one that does the SignalR stuff. So if we go and look at that, have I got it open? Yes, we have. That receives a Fibonacci series message, so that's when it's been computed, and then we'll just push it up through the signal events pusher, which then pushes it to all connected clients. And we have our Fibonacci actor, which is like our parent actor. So that takes in a reference to the client bridge actor with an I actor ref. And what's important to note is that the I actor ref, that is not a reference as in a .NET reference to an object. That's just basically the address to which we can send messages. And that then creates the Fibonacci series actor, which is the one that does the actual computation. And it will receive the Fibonacci series message once it's been computed. Oops. Which just looks like this, immutable. And it takes the source message, which it got from the queue, which just contains a number. And this is our supervisory strategy. So this is where we decide what happens when things blow up. So if it's an argument out of range exception, for example, -1, that will trigger that. It will cause the actor to restart. Otherwise, if it doesn't know what to do with it, then it will just stop it, just for the sake of demo. And if we look in our series actor, that receives the Fibonacci source message with our number, and then it computes the Fibonacci series. And then when it's done, it tells back to its sender our series. And also note here that we've got a log, so that there's a log provider that you can, or several logging providers that you can use. This one just logs out to the console, but there are lots of different ones that you can use if you want to have something else. So if we were to run this, well, we can do that first. Then we can see what it looks like. And then we can see. So you can see that this is now pushing stuff to the queue. And you can see that they're being received and they're being computed at the same time. And hopefully a -1 will appear soon. As luck would have it, this seems to take a while, but that's the joy of random numbers. But if we wait a little while, and then we should see that there are some error messages that turn up off to the left here, and this isn't going very well. Oh, there's one. And then you can see that it restarted. But the system just carries on doing its thing, so it survived that nicely. So instead of riddling your code with try catches and then trying to get back into a good state, it's really nice to be able to restart things, start at a clean slate, and then just get back to work again. So we can then have a look at the front end for this, because that's quite fun as well. So we have, how many people here have used React and Redux before and have some knowledge of? So a couple of you. So basically you have a store that has your state. No, do not take survey. And you then update the state, and then based on that, then your components are re-rendered. So we have a store here that keeps our state, and that takes in, that's in our previous state, the Fibonacci series array, and then it takes in an action which is of type add series action, which just has one of these series with it. And also here, it's important with the principle of immutability. So instead of mutating the state, what we do here, this is of course very naive and not the most efficient way of doing things, but it's okay for demo purposes. We return a new array, put the new value at the top, or at the beginning of the array, and then we spread our previous state over the rest. And then we have a component that just renders this, which is what we saw before with the numbers coming out. But the really fun part here is this piece of middleware, which is what allows us to have a message-driven architecture from end to end, all the way up to the client. So this little piece of middleware here, we then, I'll show you where it's registered afterwards, but we connect to our hub and do all of that, the SignalR thing. So if you were using a different WebSocket framework or server-sent events or something, it would be slightly different, but the principle would be the same. You connect to that, and then when your messages are pushed, then you dispatch an event or dispatch an action, and then that gets, it will then appear in your reducer that we just looked at, just like any other action that was dispatched, for example, if you clicked a button or what have you. And then going the other way, any action that you trigger, you can then intercept here. For example, if you remember in the simulator, every time you press a button to open or close a switch, for example, that triggered an action in Redux, which was then intercepted in the middleware, and then it got then pushed to the server, and then that did its thing, and then it pushed new messages back again. So you have this two-way thing, which is really nice. And that's pretty much it. So what else can we do here that's fun? So we've now got everything running on one machine, which is cool. But what if we wanted to do our computation in a different process? We can start by doing it in a different process on the same machine. So if we then look at this Akka console here, which is what we'll use to host the process, then all that we're doing here is that we're making an actor system. And note that it's not called demo actor system, this is Pi actor system. It could be demo actor system, but I've given it a different name. So you set up an actor system somewhere. This one happens to then be on the same machine. And you give it a port, and you configure the serializers. If you saw very briefly, there was a yellow message as soon as we started the demo previously in the console. And that's an error message saying that the JSON.NET serializer is deprecated and that you should use the Hyperion serializer instead. So this is what we've configured here now. And note that we're not creating any actors. All that we've done is that we've got a program that has a reference to the same project that has the actors and the messages that are being sent. That's all that we need to be able to deploy actors to it. So if we set the startup project to contain Akka console as well, and we start everything, we then get a third window. And we can now see oh no, sorry, I forgot to check out the right branch. Which is, local. There we are. So now it's listening on, and now we can see here that the messages that previously were in this one here are now being printed out in this window instead. So the actor has then been deployed. Now this went wrong, so we just continue. Of course, as luck would have it, we now have lots of -1s. And if we refresh here, we'll see that the same thing is happening as before. But if we want to do something that's even more fun, I've got this little thing here connected, and I have just copied over the same console app that I built on my machine, and you can see here that I'm just running it in mono, and now it's waiting for things to be deployed to it. So if we then remove, and this time I will remember to check out the right branch. And start things again, you will then see takes a little while. Now the message or the actor has now been deployed to the Raspberry Pi, and that could of course be any machine anywhere in the world, and the system is still doing its thing. We can refresh here and watch it compute. And as soon as we see the -1 here, it will supervise and restart and recover just as it was doing before. So that more or less concludes the demo. So what have we learnt? That we can use a system, or we can create an actor model that is distributed over different machines, and it is very useful for making processing pipelines. So you have messages in, you need to process them somehow, send the result on, and it lends itself well to scaling both vertically and horizontally, where you can deploy many actors horizontally, or you can deploy to a machine that has more oomph. We make systems that can stay available even though things go wrong. And yeah, there are some resources here. The Gitter is really, really good. The core contributors are active there. And there is a good free bootcamp on petabridge.com, which is the company that actively supports Akka. And then I'm not even going to try and pronounce that name, I'll just butcher it. But he has a very, very good blog on Akka with both examples in C# and in F#. And then there are also some nice Pluralsight courses. So that's pretty much it. Any questions? The one there?
Yeah, I have a question. The code that you have, can you share that one?
Yeah, sure. I'll stick it on GitHub later on this evening. The slides as well. Any others?
Maybe another one. What is the most recurring issue that you found during the whole project when you used it?
It was a bit difficult to start with the remoting and getting it to, because we have two things that start simultaneously and they both need each other. So that we solved that quite elegantly using behaviors, so that they both went into the connecting state, and then when that one found that one, then that stopped going into the connecting state, and then it found the other one. So that was probably one of the tricky things, but yeah. Anything else?
Yeah, one more question. Since all the actors are in one process, how do you deal with, let's say, message overflow? Meaning the mailbox's size growing to a the sizes?
Well, as with any machine, like you have a finite amount of memory. So if you,
Yeah, but for some systems, you can, let's say, use external queuing.
I don't know what you could do about that if they've built in any solution for that. But I can find that out for you if you want.
Come see my dog.
He knows.
Room 2.
Anything else?
I got it. So, as far as clustering goes, how often did you get situations with split brain or partitions where one system couldn't talk to the other? And as far as your setup goes, was it in the cloud or was this on premise in terms of the machine that you're running?
This is in deployment, so this has only been running on just on our machines so far. So we haven't run into those issues yet. But they are things that we'll need to look into further on down the road. Absolutely.
Could you repeat the questions?
Oh, yes. Well, I can. He asked what the most common problems that we had, and one more problem that we had actually was that in the beginning we sent each change in the simulator as one message over signal R. And that worked all right when you had a small electrical model, but it didn't really scale very well. So we had to cut back on that and batch things a bit because it just overwhelmed the front end. It just froze. But even now, when we've got, I don't know, 1,000 messages or something, and then we batch them up, and it even every 10 milliseconds, it's running quite smoothly. Well, thank you all for coming. Oh, one more.
Could the actor model also be a replacement for other event boss-driven models like, or we have an application that has many nodes, but they are really dedicated services, and that gets complicated when the customer does not want to have so many things to deploy and things like that. Would that be an option perhaps that we should look into?
I suppose it could be, but I don't have experience with large systems like that, so it'd be hard to give any definitive advice. Yes.
Come see my dog.
Well, thank you very much. It's been a pleasure.